Here we have the function f of x equal to 0.1 x to the third plus 2, and we want to find the area of the region bounded by the graph, between the graph and the x-axis, and from 0 to 3. So this is the graph for f of x equal to 0.1 x to the third plus 2. And for the interval from 0 to 3, we choose to partition this interval right here as follows. X of 0 will be a, which is 0, and then x of 1 will be 3 times 1 squared divided by n squared, where n squared is the number of subintervals. And so if we have 8, if we fill this up with 8 rectangles, then n would be 8. And x of 2 will be 3 times 2 squared dividing by n squared. X of 3 will be 3 times 3 squared dividing by n squared. And then x of n is 3 times n squared dividing by n squared, which is equal to 3. And once more, whatever partition we choose, the x of 0 must be a, and the x of n must be b, so b is 3. And therefore, with this type of partition, in general, x of I is 3 times I squared dividing by n squared. And again, n squared is the number of rectangles. And so let's say we have 8 rectangles. We'll fill this shaded region with 8 rectangles. And so now the shaded region is filled with 8 rectangles. And the first x of 0 will be 0. And then x of 1, which is right here, it'll be 3 times 1 squared divided by a squared, since n is 8, and that comes out to be 0.046875. And then x of 2, which is right here, it'll be 3 times 2 squared over 64, and that will be 0.1875. And then x of 3 will be 3 times 3 squared dividing by 64. And then x of 4 will be 3 times 4 squared dividing by dividing by 64. That comes out to be 0.75. And so on until we get to this is x of 7. X of 7 is 3 times 7 squared dividing by 64, and that's 2.296875. And that's what this is, 2.296875. And then last, the x of 8 would be 3 times a squared dividing by a squared, which is 3, because the last right here has to be 3. And now let's talk about the widths of each rectangle. The first width will be x of 1. So this is x of 0 and this is x of 1. And so the width would be x of 1 minus x of 0. But x of 0 is 0, and so it will be just x of 1, which is 3 dividing by n squared. And again, n is the number of rectangles. So if n is 8, then this would be 3 over 64. And the width of the second rectangle will be from x of 1, be x of 2 minus x of 1. X of 2 is 3 times 2 squared divided by n squared, and x of 1 is 3 times 1 squared divided by n squared. And this comes out to be 9 over n squared. And the width of the third rectangle will be x of 3 minus x of 2. And that comes out to be 15 over n squared. And then the fourth rectangle will be x of 4 minus x of 3. And that comes out to be 21 over n squared. And again, if n is 8, meaning 8 rectangles, then this will be 9 over 64, 15 over 64, and 21 over 64. But we want a general formula with n, and so this delta x of y is the width of the ith rectangle. It would be x of y minus x of y minus 1. And earlier we said that if this is the partition that we chose to have this partition, then it means that x sub I is 3I squared over n squared. And so in the place of x sub I, we have 3I squared over n squared. And then x sub I minus 1, it means just replace the I with I minus 1. And so this is x sub I minus 1. And then this will be 3I squared, and then this is 3 times I minus 1 is I squared minus 2I plus 1. And then simplify by multiplying this out, we get 3I squared minus 3I squared plus 6I minus 3. And then 3I squared minus 3I squared is 0. And what's left is just 6I minus 3 and divided by n squared. So this is the formula for finding the width of the ith rectangle. And so let's say we want the width of the 8th rectangle, then it'd be 6 times 8 minus 3, which is 45, over n squared, which is 64. For this particular example, if we want the width of the 7th rectangle, then it'd be 6 times 7, 42, which is 42, and minus 3, which is 39, and then over 64, and so on. And for this particular partition, for division of the, how we divide the subinterval, how we divide the interval from 0 to 3, the last rectangle has the largest width. And the largest width of a partition, we call it the norm of the partition, and is denoted by the double bars with delta inside. So this double bars with delta is called the norm of the partition, and is the largest width of a partition. And in this case is width number 8, is the width of rectangle number 8. And right here this is 3, and this is 2.29687. And so the width of the 8th rectangle is 3 minus 2.29685. And that comes out to be 0.703125. And notice that if we allow the largest width, so this is the largest width of all the widths, if we allow the largest width to run to approach 0, and there will be an infinite number of rectangles, and that's the only way that could happen in order for the largest width of the norm of the partition to go to approach 0, is to have an infinite number of rectangles inside the shaded region. And therefore, if we allow the norm to run to 0, then the number of rectangles or the number of subintervals will run to infinity. The converse is not true. There are examples where n would run to infinity, but the norm or the largest width does not run to 0. But anytime the norm runs to 0, then n will run to 0. And now let's find the areas of the 8 rectangles and see approximately what the area of this shaded region. And then after that, we'll fill it up with an infinite number of rectangles and get the exact area of the shaded region. And these are the widths of the rectangles. And so width number 1 is x of 1 minus x of 0, and so it'd be, once again, we did this a little bit earlier, so it'd be x of 1. And so let's zoom in a little bit. So this is x of 0 and this is x of 1, and the width here is 0.046875. And then the width of the second rectangle is 0.140625. And then width of the third rectangle is 0.234375, and then so on. So these are the widths of the 8 rectangles. And now let's calculate the height of the the height of the rectangles. So let's look at the first rectangle. On the first rectangle, this is 0, x of 0 is 0, and this is x of 1, and x of 1 is 0.046875. And we will use the right endpoint, which is the 0.046875, to find the height. And the f of 0.04685, and again, the function is 0.1 times x to the third plus 2. And so in the place of x, we put 0.04685, and we will get approximately 2. And so the height of the first rectangle is 2. The second rectangle, x of 1, is 0.04687, x of 2 is 0.1875, and we will use the right endpoint, which is the 0.1875, to find the height of the second of rectangle number 2, and that comes out to be 2.0659, and so the height of the second rectangle is 2.00659. And similarly, the heights of the other 6 rectangles are these values right here. And now that we have found the heights and the widths of the rectangles, then we can find the areas. So the areas of the rectangles would be these values right here. And then add them up, and we get the 8.96 right here. But notice that the rectangles, they are outside of the shaded region, and therefore the figure 8.96 will be higher, much higher than the actual area of the shaded region, because these rectangles right here, they are outside of the shaded region. And so now let's fill this up with more rectangles so we get a better approximation. And now instead of 8 rectangles, let's fill it up with 50 rectangles. And so first we need to find the x of i's. So this is the x of i's right here, and then get the area. And so this is 50 rectangles. And again, the last rectangle still has the highest width. And now we got 8.16. And then now let's fill it up with 100 rectangles. So generate the x of i's and then find the areas. So there's the 100 rectangles. And then we got 8.09. And then now let's fill it up with 1,000 rectangles. And so with the 1,000 rectangles, we get 8.03. And now let's fill it up with an infinite number of rectangles. And as shown earlier, this is the partition that we have chosen for this interval. We chose to divide this interval into subintervals using with this pattern. And so x of I is 3i squared dividing by n squared. And then earlier we also found the formula for the width of the ith rectangle. And so the width of the ith rectangle is 6i minus 3 dividing by n squared. So this is the function we're dealing with, is 0.1 x to the third plus 2. And again, we will use the right endpoint method. And so this is x of I, this is the width of the ith rectangle, and so f of x of I is the height of the ith rectangle. And so f of x is 0.1 x to the third plus 2, and so f of x of I will be 0.1 x of I to the third plus 2. but x sub I is 3I squared dividing by n squared, and then plus 2. 3 to the third is 27. I squared to the third is I to the sixth. We just multiply the exponents here. And then n squared to the third is n to the sixth. You just multiply the exponents and then plus 2. 0.1 times 27 is 2.7. And so we have 2.7 I to the sixth over n to the sixth. And now let's get a common denominator so we can combine this with the 2. So 2 is the same as 2n to the sixth dividing by n to the sixth. And common denominator is n to the sixth, and then we have 2.7 I to the sixth plus 2n to the sixth. And so this is the height of the ith rectangle in terms of n. And now let's get the area of the ith rectangle. And so it would be the height times the width. This is the height. And then the width is 6I minus 3 dividing by n squared. So this is the height, this is the width of the ith rectangle. The bottom n to the sixth times n to the second is n to the eighth. And then the top, we just multiply this out, and it'll come out, it comes out to be 16.2 I to the seventh minus 8.1 I to the sixth plus 12n to the sixth times I and minus 6n to the sixth. And now let's separate these terms. So this will be the same as 16.2 over n to the eighth times I to the seventh. And this will be in minus 8.1 over n to the eighth times I to the sixth. And then right here we have 12, and then n to the sixth dividing by n to the eighth, we get n to the second, and then this is times I. And then 6n to the sixth dividing by n to the eighth is 6 over n to the second. And so this right here, this is the area of the ith rectangle in terms of n. And so if we have n number of rectangles, then it'd be just summation from 1 to n. And so if there are 8 rectangles, then n would be 8. If there are 100 rectangles, then n would be 100, and so on. And so it would be f of x sub y times delta x, which is this. And so that's what we have right here. And then this is summation of sums and difference. And so we get to rewrite it like this. And so it will be the summation of this term minus summation of this plus summation of this and minus summation of this. This is the constant because the summation is with respect to I. And this right here, there's no I. So we can place it in front of the summation sign. And then same thing here, and same thing here. And this is a constant. There's no I here. And so this is summation of this expression right here, and there's no I. So it's just like doing summation of a constant. And recall that if we have a summation of a constant, then it's just the constant times n. And so this particular summation right here is just going to be 6 over n squared times n. You can think of it as constant, because the summation is with respect to I, and there's no I here. And then we need a formula for summation of I to the 7th, and also I to the 6th, and summation of I. And these are the formulas that we'll need. Summation of I is n squared divided by 2 plus n over 2. And then summation of I to the 6th is this. And then summation of I to the 7th is this. And so in the place of summation of I to the 7th, we'll replace it with this. And then this summation of I to the 6th, we'll replace it with this. And then summation of I will replace it with n squared over 2 plus n over 2. And so that's what we have right here. So it'd be 16.2 over n to the 8th, and then this is summation of I to the 7th, and then minus 8.1 dividing by n to the 8th, and this is summation of I to the 6th, and then over plus 12 over n squared, and then times, this is summation of I. And then that last term was the summation of this constant, so it's times n. And then multiplying this out, then we get this line right here. And then multiplying the second line, multiply this out, then this is what we get. And then the last line, 12 over n squared. Let's do a couple of these first. 12, this is 16.2 over n to the 8th times 1/8 n to the 8th. The n to the 8th will drop out, and what's left is 16.2 over 8. So that's what we have right here. And then 12 over n squared times n squared over 2, that's the 6 right here. That's what we have. And so this right here, this is the sum of areas of n number of rectangles. And now we want exact area of the shaded region. And so we need to allow n to run to approach infinity. And we can do that by allowing the norm, or the largest width, to run to 0, to approach 0. So we allow the norm, or the largest width, of the partition to approach 0, and that means there will be an infinite number of rectangles, or infinite number of subintervals. And so now n approaches infinity, then we get 16.8 over 0.2 over 8, and as n approaches infinity, this term will go to 0, 0, 0, and 0. And then all of these right here will go to 0, because they all have an n in the denominator, and n is approaching infinity. And then this, the third line, we will get 6, and then this will go to 0, and this will go to 0. And so the 16.2 over 8 plus 6 is 8.025. And so the exact area of the shaded region is 8.025. And so this limit quantity right here, where we allow the norm, or the largest width, to approach 0, is equal to 8.0625. And this limit quantity, when it exists, this is the symbol that we use to represent it. It's called the definite integral from a to b, where a is 0 to 4, because our shaded region is from 0 to 4. And then f of x is the function, 0.1 x to the third plus 2, and then times the differential of x, which is dx. And so once again, this quantity right here, the limit, this limit quantity, is represented by this definite integral. And we know from here that it's equal to 8.025. And so this symbol, f definite integral right here, is equal to 8.025. And this is the area between graph and x-axis. And so that's what this definite integral represents, is the area between the graph and the x-axis. And in summary, when we fill this up with 1,000 rectangles, we got 8.03 for the shaded region. The exact area of the shaded region turns out to be 8.025. So this is very, very close.